that it's their fault that you don't understand stuff. So anyway, yeah, this is all what I'm going to teach. If you've gone through my book or I've ever taken my class, it's very similar in style, but it's a progression on top of what you've already learned in the book or in the class. This is HD Wallets, BIP32, BIP44, BIP39.
Jimmy, can we get your GitHub again?
It's Jimmy Song, Learn HD. So Learn Hierarchical Deterministic Wallets. So let's see, there's 8, 12, 6, 14, 19, 25. Wow, this is a big class. All right. It's going to be hard, but you know what? I'm up for the challenge. Yeah. So look up when you're like all set up and have everything ready, because then we can get started. And we've capped the class and closed the door so no one can come in. You also can't leave until you're done. Jimmy Song Learn HD. As you can see, it's very old. It's 19 hours old. All right, just I want to get a lay of my audience. How many of you have gone through my book? Okay, how many of you have taken my class? Okay, how many of you can code Python? All right, you definitely kind of need to know at least that one. And how many of you are familiar with Jupyter? All right, that's enough of you. Okay, all right.
Jimmy, I have a dumb, maybe not a dumb, but I have a Python question. There's like Python and Python 3.
You need Python 3.8 or higher.
What about pip? Is it pip 3 also?
Yeah, it should be pip 3 if it's Python 3, so yeah. Find like a hosted Jupyter instance or something. Like the setup part's a little bit annoying. Okay, who's set up with Jupyter? All right, so you guys are still working on a bunch of you. All right. If you are finished setting up, try to help other people that haven't set up, so you guys can get to know each other and stuff.
Yeah.
So yeah.
Yeah, I don't think you
It is
Yeah.
Do you know if we can run this just out of Anaconda?
Possibly, but you just have to have the requirements installed and as long as the Jupyter notebook's running and it's pointing at the right library, you should be fine. Yeah. It should, I've had people run it on Anaconda at work, so I don't see why not. At some point, I'm gonna like transition all this to Replit or something. Make it easier. So you, once you install, you should have, and you should get a browser with this. You want to click Session, and then click Session again, and then you get to the Jupyter notebook that we're going to be working from. Also, if you want to take the annoying thing, Cell Toolbar off, go to Cell Toolbar and click None, and that will take the little thing off that you don't really need. It just sort of like litters your screen a little bit.
You said click Session and Session again. It's Session IP.
IPYNB, yeah. IPython notebook is what that stands for.
Once I get yeah, so then yeah, just type Jupyter, just put chat set Jupyter. Come on, baby. No, looks good. Yeah. So happy. I'll go the other way next time.
You're happy that you have it set up then?
Yes.
Okay. Yeah. Well, that's accomplishment number one, is setting up your environment. And there's going to be a significant amount of that sort of thing. Again, the slides I'm going to use are in your Jupyter notebook, so you don't need to flip back and forth. In fact, they're like generated directly off of the Jupyter notebook. There's like a little command that you can do, which is kind of cool. Little thing I learned. But yeah, we're going to get to this. All right, so everyone's set up? Almost? Who's not set up?
I'm having problems, but you don't have to
Okay.
wait on me. Come back up.
Okay. All right. Okay. I'm gonna get started a little early, just because my suspicion is that this is probably going to be more material than 2 hours, just given the complexity of the topic and so on. So first part will be a little bit more lecture to give you an idea of what's going to happen. But yeah, you will be coding yourself, and HD Wallets, BIP32, all that stuff. But here are the objectives for me. It's to teach you these things. Learn HD Wallets, which is defined in BIP32. Learn HD Wallet Organization, which is defined in BIP44. Learn mnemonic backups, which is defined in BIP39. These are all things that you can go look up. You should go to the BIPs repository and read them afterwards to see if they make sense to you. And yeah, finally, we'll create some wallet seeds that you probably are all familiar with, right? Like creating a wallet seed, the mnemonic backup words, and so on. All right, so we're going to talk about HD wallets. Okay, HD stands for hierarchical deterministic wallets. How many of you guys are familiar with these? Okay, so you've all used them, right? We're going to get into the weeds and explain how all of it works. All right. So just a couple things before we move on. I want to encourage all of you to help each other, and it's okay if you get a little bit lost and so on. There's a directory under session called Complete that has all of the answers. So if you need help or whatever, there's not too much shame in going and looking it up because you can't keep up or whatever. It's meant to be fast, okay? And it's meant to be done in a way where you can go home and review this material and try it again on your own. Right now, it's mostly just to get the mental hooks in your head and make sure you have enough knowledge of this stuff that you can reproduce it later when you actually need to go implement it when you work at a wallet company or something. Anyway, that's what we're going to describe. All right. So what's the motivation for hierarchical deterministic wallets? Well, the motivation is that reusing addresses compromises privacy. So if you use the same address over and over again, people are going to know all the stuff that you're doing. And also, creating a new private key for each transaction means that you have to back it up. And that's very annoying too, right? If you create a new private key every single time, you'll have a new address every single time, but you also have to back up your private key. And actually, if you look at the core wallet, that's how it used to work. The original client would generate 100 private keys at a time. So if you went over 100 private keys, and you had a backup of the first 100 private keys, but then you generate another 100 private keys and you didn't back it up, then you would have no backup. So some funds were lost this way, which is pretty unfortunate. So that's not great user experience, right? And backing up a lot of private keys is not easy to do on paper. Right? Like if you're trying to back up 100 private keys, you have to have 100 with strings that you have to back up all of. That's not great UX either. To enter each and every one of those. So that's the motivation behind what became known as deterministic wallets. The idea of deterministic wallets is that you can use a single seed to generate lots of private keys. A single seed to generate lots of private keys. And generally the way deterministic wallets work is that the n plus first private key is generated from the nth private key. So you have one private key and you use that to generate the next one in some deterministic fashion, and you do the same, and as long as you have the first one, you can generate as many as you want. And this was actually implemented in Armory, which was one of the first wallets to use deterministic addresses back in 2012. Fun fact, I used to work there. I was the VP of engineering way back when. But that was the first sort of iteration of deterministic wallets. Now, what's wrong with deterministic wallets? Well, here's a naive implementation of what a deterministic wallet looks like. You could do some secret E times G, which is P. So you have a secret times the generator point, and that equals the public key. And you could just do E plus 1 times G, and as long as the recipient, the sender has P, they can just add G and get the public key for the new one. So you can do this pretty easily, and you would have many different addresses. Now, what's wrong with doing this naive deterministic wallet? Well, it's really nice because you just store one private key and reveal the public key to the payer, and you can have as many addresses as you want. But you have zero privacy from chain analysis or the payer, because they could just keep adding G to the public key and see if it hits something, and that's very easy to do. A more robust deterministic wallet looks something like this. EG equals P, and C is a shared secret, H is a hash function. So what that means is that you have a private key and some shared secret between you and the pair. and you hash the shared secret, public key, and the number 1 to get the first public key. And they can derive it because the math works out. They can determine h of 1 plus p times c and so on. And it's both sides can determine the public key, which means that both sides can determine the address. And you get privacy from chain analytics because they don't know what the next address is going to be, but you have no privacy from the pair. The pair can determine all of your addresses because they have the shared secret. So before we go on, I need to tell you what message authentication codes are. Basically, it's a cryptographic construct to verify that a message is authentic when you share a secret already. So we already do this with public key cryptography when you sign a message and you can determine that it's authentic. But if you're not using public key cryptography, instead you have a shared secret, both of you have the private key essentially, you can use something called message authentication codes, or MACs. And they are a way to sort of deterministically put something at the end to say, okay, this message has a MAC, so it comes from somebody that knows this shared secret. Okay, it's kind of like signing, but it's used with a shared secret and not public key cryptography. HMAC is an implementation of MAC where H stands for hash-based. So hash-based message authentication codes are where you share a secret and you use hashes to deterministically verify that the message was made by somebody that also shared the secret. So if you and I share a secret, then you put a MAC at the end of it, I know that the message came from you, and we don't need to do more complicated public key cryptography signing. Most cryptographic hash functions have an HMAC implementation. So SHA-256 certainly has one, and almost all cryptographically secure hash functions have it. All right, so using HMAC, we can do something called hierarchical deterministic wallets, which is BIP32. Now, what is it? The idea is that instead of having a single chain of deterministic private keys, you have layers of deterministic private keys. So you get an entire tree of many, many, many private keys. So you have a single seed and you have a hierarchy. And as long as you know the hierarchy, you can determine new Bitcoin addresses and so on. And it gives you all sorts of nice properties. The master private key can generate 2 to the 32nd child private keys. So at each layer, you can have 2 to the 32nd, or about 4 billion children. And each child can have 4 billion children. So, I mean, you can have essentially an infinite number of private keys from a single seed. Revealing a child public key, importantly, does not reveal the parent public key, right? So if you have the child, you can't determine the parent, but if you have the parent, you can determine the child. So it has this asymmetry there. And it adds privacy from the recipients. So payers don't know all of your stuff because they have a narrow slice of all of the possible addresses that your seed has. So that's how it works, and it's better than a straight deterministic one, because a straight deterministic one is linear and doesn't have levels. This has multiple levels, and you only reveal a particular slice. Yeah.
This sounds like derivation paths.
Yeah, that's exactly what that is. Yeah. Each path component is one of 2 to the 32nd. All right, so here's the actual implementation. EG equals P, where E is the private key and P is the public key. And C is the chain code. And you guys might have heard of this word, chain code. There's Chain Code Labs, which is named after this, kind of like Coinbase is named after the Coinbase transaction and stuff like that. But the chain code is sort of our shared secret from the HMAC, and H is the HMAC SHA-512 function. HMAC SHA-512. SHA-512 is very much like SHA-256, except it spits out 512 bits instead of 256. And it's part of the SHA-2 family of cryptographically secure hash functions. And you have 2 to the 32nd possible children at each level. And the way it works is that you have half that are hardened keys and half that are unhardened keys. And I'll explain the difference in a bit. Hardened means that the public key and chain code cannot be derived just using the child pub key. So if you have the child pub key, or if you have the parent pub key, you cannot derive the child pub key if it's hardened. But if it's unhardened, you can derive the child pub key. So it gives you some level of privacy depending on which side you want. And so we'll see what that means. All right, so here's how you define a hierarchical deterministic public key. You need a public key, a normal ECC public key, which is 33 bytes in the compressed sec format. Everything has to be compressed sec, by the way, no uncompressed anywhere. The chain code is a 32-byte shared secret with pairs, okay? Depth is 0, 1, or 2, and it's the level at which the hierarchy is. So the master seed is at level 0, its children are level 1, its grandchildren are level 2, and so on. The fingerprint is 0 for root, or the first 4 bytes of the parent pub keys hash 160. So this gives you sort of like an idea of where this key is derived. And the child number is the ordering from parent. So it could be anything from 0 to 2 to the 32nd. So it's some number between 0 and 2 to the 32nd, which is the number child that you are. All right, and the private key is the normal ECC private key, and to keep the lengths the same, they made it 33 bytes even though you only need 32 bytes. You might remember that the private key is a 256-bit number. So 33 bytes is actually 1 byte more, but sec format is 33, and to keep the lengths the same, that they made it that way. Chain code is 32-byte shared secret with the pairs. Once again, depth, fingerprint, and child number are exactly the same. So the only thing different than an HT public key and an HT private key is the initial public key or the private key of the point that you're using. The chain code is essentially the same and so on. Yeah?
Is this the one on the previous slide? Is that the same thing as an Xpub?
Yeah, so this is an Xpub and this is an Xpriv, and you'll see how they all. Xpriv is sort of like a particular format that's a base 58 encoded, but this is all the data that's in an XPRV, and this is what's included in an XPV.
So you normally don't give your Xpub to another person?
No, you don't, unless you want them to know, unless they're paying you on a regular basis and you want them to use a different address each time, you don't typically give an Xpub.
When was all this invented?
2013.
So it was invented specifically for Bitcoin?
Yeah, it's part of the BIP32 spec. Yeah. Yeah.
Can you touch on the 33 bytes piece? You said that like in order to keep something similar to some of the things.
Yeah. So you'll see that this is 32 bytes. This is 33 bytes. Like, and this has to be. This is, I think, 1 byte or 4 bytes. I can't remember. I'm pretty sure it's 1 byte. Fingerprint is 4 bytes. The child number is also 4 bytes. So you add it up. I think it's 78 or 65, 66 plus 8, 70, 74 or something like that. And then there's a version thing for 4 bytes. So it's 78 bytes. So this is 78 bytes. In order to make this also 78 bytes, the normal private key can be encoded in 32 bytes, but they made it 33 so that they would be the same length in terms of bytes. and you'll see like after you base 58 encode it, it has the XPUB prefix because of the version. Yeah.
I'm still a little confused about what the chain code is and this shares.
Yeah. So we'll get to
Okay.
it. We'll get to it. All right. So the process for generating a master HD private key is create a seed of 128 to 512 bits, and you calculate H, which is the HMAC 512 of this D and the seed, and the D is always this string, exact string, Bitcoin seed. It's part of the spec. And it has to be Bitcoin seed. The master secret is the first 256 bit. Remember, HMAC SHA-512 will spit out 512 bits. You take the first 256 bits, and that's your master secret, and the next 256 bits is the master chain code, and those are all going to be part of your master XPRV, basically. That's what's required. All you need is a seed. So you can actually have a Brain Wallet HD seed if you wanted to. It's entirely possible. Not many people know about that. They think it has to be, a bunch of seed words or something like that. You can actually make it, and I'll show you exactly how in a second. So here's an example of the master key generation. So you're going to need the private key object or class from ECC. We also have big endian to int, HMAC SHA-512, raw decode base 58, and HD private key, which we can take a look at real quick. So if you go to Jupyter and go to hd.py, you'll see that HD private key has a bunch of these things that we talked about. You have the private key, the chain code, the def, the parent fingerprint, the child number, and whether or not it's testnet. These are all components of a hierarchical deterministic key. And there's like a serialization and stuff that we'll get to as well. But that's what an HD private key looks like. And I'm going to make a Brain Wallet seed. I don't recommend you generally that you do that, but that's what it is. Yeah.
Is Bitcoin seed, is that the passphrase?
Well, that's a requirement as part of your HMAC.
Okay.
That, again, it's part of the spec, and it's literally exactly that string, and you have to know about it, right? And that's kind of how it is. And HMACs require this. So you do HMAC 512 on Bitcoin seed, and then your seed phrase, which in my case is Jimmy at programmingblockchain.com, Jimmy Song, and then you get the result of the HMAC SHA-512. You take the first 32 bytes, and that's your secret for your private key, and the last 32 bytes are the chain code. Now you have the private key and the chain code. That's enough to make a master private key, if you see this, the depth is going to be 0 by default, right? Because if it's the master private key, then it's the root one, which is at the very top. It doesn't have a parent, so the parent fingerprint is all zeros, and the child number is going to be 0 because it's the root one. So everything else is determined for you, and we can have a master private key. And you can print out like the BIP32 address associated with that particular key, which you can do in your Jupyter notebook. So here's the example master key generation, and if you do it, you get TB1Q7KN, and if you're familiar with BIP32 addresses, this is a single key locked BIP32 address, right? Pay to witness pub key hash, and that's what this looks like, and this is how you generate a master key, and at each node in this master child is going to have a private key, its grandchild, like however many levels you go down, every single node in this huge tree has a private key, and you can ask for the address. By the way, you can go to hd.py to see exactly how the address is determined, but it's let's see. So get address is, let's see, it's in HD public key, which has very similar. Where is HD public key? Yeah. That's the test. Yeah. No, I lost where it was. Yeah, there it is. Okay, so it has all of the same elements, except instead of a private key, you have a public point, right? That's the only difference in HD public key. And using that point, you can get the address, including the BIP32 address, pay to script hash, pay to witness pub key hash address, or like the normal pay to pub key hash address. Any of those things are available using that point because there's a point associated with each one. Anyway, that's what master key generation looks like. So here is exercise 1, and you can go to your Jupyter notebook. Make sure you run this one, run this test cell, because everything else works off of that. And then if you click this link, this test, that will take you to hd.py. And the thing that you want to do is the from seed method or class method. So if you scroll down, where is the from seed? A little bit tricky to go and find. Parse.
79.
What's that?
79.
79? Yeah, there it is. So I did I already do it for you? I think it might have gone through. Yeah, that's unfortunate. I thought oh, you know what? I didn't. All right. So anyway, try to erase it and do it again. Right? Like it's gonna pass, isn't it? Right, let's just see. Yeah. All right, so if it doesn't pass, then something's wrong. But basically, what you want to do is, I'm going to, if I save it like this, then this isn't going to work because there's an error. It doesn't have a bunch of these things. What you want to write is this method from seed, which is h equals HMAC SHA-512 of Bitcoin seed. This literally has to always be there. And then the actual seed that you got from the method. And then the private key is a private key of the first 32 bytes being the secret. And then the chain code is the last 32 bytes. And then you return an instance of the class like so because it's a class method. So that should work here, except not all arguments converted. Oh, you know what? That's not right because I'm passing. Private key requires a number, and I'm passing it bytes. So we need to convert it from big endian to an integer. And now it should work. Yeah, now it works. So it has to go from big endian to an integer. So this is sort of like an example of how you create a master private key from any sort of string, like that, or any number of bytes. You use HMAC SHA-512. It splits it into 32 bytes of a private key and 32 bytes of a chain code. And then that creates a master private key. Yeah.
Just like there's the concept of the passphrase, like
Uh-huh.
Cold Card has it. Where does that fit in? Is that just
That's later. So
Okay,
we'll,
okay.
we'll get to mnemonics and BIP39. Right now, I'm just showing you the BIP32 spec, which requires a seed. And this from seed method is going to be used as part of BIP39. In fact, the seed that you get here is going to be deterministically generated from your seed phrase. So that's how. This is sort of like a fundamental part of why I'm teaching it to you first.
and then just what the concept of account number is
Mhm.
that
Well, that's part of BIP44, so we're
Okay,
not there
okay.
yet. So we're just learning how to deterministically generate private keys. That's what we're learning. All right, so that's exercise 1, and this is the part that makes all of the hierarchical deterministic wallets work, and it's child derivation. It's the ability to create children off of the master or off of a parent, and you have as many private keys as you need at any level. So here's how you derive the child key. You have EG equals P, where E is the private key, and you have H, which is HMAC SHA-512, C is the chain code, and I is the child number. So you want to determine the ith child off of a particular parent. H is the derivation source. So for hardened children, H is going to be C, E, and then concatenated with I. So we're going to do an HMAC SHA-512 with the private key in there. So this can only be derived if you have the private key. Unhardened children, you can derive it with the public key. So this is the big difference. Hardened children, you can deterministically get only if you have the private key. For unhardened children, you can deterministically get with either the public key or the private key. As long as you have unhardened children, you're able to derive, if you have the Xpub, you can derive the unhardened children just as much as the private key owner. This gives, the hardened one gives you more privacy. And in fact, with Bitcoin Core, if you're using BIP32 wallets, they do hardened derivation of absolutely everything. So you can't deterministically figure out just with public, with an Xpub or something, what's going on.
So does the ability to have unhardened children give you the ability to like give an address to someone who's going to pay frequently?
Yeah, that's the idea.
Is that BIP85?
It's not BIP85. It's part of BIP44. But I'll show you. So here's how you derive the child's private key. The private key of the child is equal to you get this hash result, and HL, which is the first 256 bits of H plus E. So that way, it's related to the parent with E, but you add exactly HL to it. And the public key of the child, if you do the math, is HL times G plus P. You already know P, and if it's unhardened, then you can determine H, which means you can get HL. So you can also get the public key of the child. But if it's hardened, then you can't get HL, so you can't determine what the public key of the child is. So that's the big difference. You can derive the P child with unhardened children only. The chain code of the child is HR, or the last 256 bits of H. And you notice that the chain code is used as part of the hash, right? So that's how you use the shared secret as a way to keep doing HMACs on these levels. It essentially ends up being like your own personal hash function that uses C. All right, it's a lot that I just threw at you, but this is how you derive the child secret, right, for that particular level, and the child chain code, and the rest of it is deterministic because you know the depth is going to be one more than the parent. You know that the parent fingerprint is going to be a certain thing that's based on the parent. And you know the child number that you were deriving, which is I here. So based on that, you can determine the child. So here's what that looks like. Here's unhardened child derivation. ECC, import N, N is the order of the group. We have the HD private key. We need big endian to int, HMAC SHA-512 into big endian. This is the reverse. And we have a seed phrase. We're going to make the master, and we're going to get the 0th, or the very first child of this master. So what do we do? Well, the data is going to be the private key. For unhardened child derivation, we need the public point in sec format, and then the index in 4 bytes. Okay, so, whoops. If you remember, it's E, well, for unhardened, it's P and then concatenated with the child index. So that's what we're doing here. This is the public point and then the child index in 4 bytes. Then we're going to do the HMAC SHA-512, which needs the master chain code and then this data. And that's going to give us 512 bits. 256 of those bits, or the first 32 bytes, is going to be used to derive the new secret. You add it to the master private key, and you get the secret. And then the chain code is going to be the last 32 bytes. So based on the private key, the chain code, the depth is going to be 1 more than your parent. The parent fingerprint is deterministic, and you can just go get it from your parent. And the child number is the index. In our case, that's 0. And whether or not it's testnet is going to be the same as whatever your parent is. This gives us a new HD private key, right? And you can do the same thing for another layer of child and so on. And you know, you can have for whatever child you again have a private key, so you can do a BIP32 address or a pay to pub key hash address, or a pay to script hash, pay to witness pub key hash address, or even a pay to taproot address. All of these, this is how you derive the child. This is for unhardened. For hardened, this would be different because you need the private key instead of this thing. And that's you would have to cast it from integer to a big endian. All right, so the hardened key looks almost exactly the same, except the index has to be greater than 2 to the 31st. So the top bit is going to be 1, which means that the index looks something like that. And what you get is you have to take the private key secret and cast it into 33 bytes. And then you do into big endian on the index, which is this number here. This is 2 to the 31st plus 2. And you do the same thing the rest of the way. So you derive the hash from HMAC SHA-512 using the chain code as the shared secret and this data right here. And then the secret is going to be, once again, the big endian to int of the first 32 bytes plus the master secret, or the parent secret, and modded by n. And you can get the hardened child using the private key, the chain code, depth, parent, and everything else. And you can, once again, derive addresses from that private key as necessary. Now, the nice thing about the unhardened child is that you don't need the private key to derive it. If you had just a point, all of the rest doesn't require the private key. Well, you can't derive the HD private key, but you can derive the HD public key. And that's the main sort of like advantage that we have. I have a feeling this one's also written for you, but let's see, go to child. Yeah, it's all written for you. Oh, gosh, I forgot to delete all of the things. But
It makes it easier.
Yeah, like basically you're hearing what I'm doing here, but basically if you want to get a child at a particular index, everything above 2 to the 31st is going to be hardened. Everything under 2 to the 31st is going to be unhardened. And that's what this first part does. So that's 2 to the 31st, 1 left shifted by 31 bits. That's 2 to the 31st. If it's greater than or equal to 2 to the 31st, then the data that goes into the HMAC SHA-12 includes the private key and then the index. Whereas if it's below 2 to the 31st, it's the public key and then the index in 4 bytes. And we run a HMAC SHA-512 using the chain code as the shared secret and the data, and you get HMAC. So based on this HMAC, you can derive the new secret, which is the first 32 bytes, big endian to end, plus the current secret modded by n, and you can get the private key object off of that. Then you can get the chain code, which is the last 32 bytes. The depth is going to be 1 more than the parent. The parent fingerprint is going to be the fingerprint of the parent. And then the child number is the index. And you can create an instance of the class where it gives you the child. So this is the whole child derivation schema. Okay? And this is all defined in BIP32. This is how you derive the child. From the private key, HD private key, you get the private key child. Now for the public key, there's also a child method down here somewhere. Xpub. Yeah, here it is. If it's greater than 2 to the 31st, then you raise an error because you need the private key in order to derive a hardened child. For an unhardened child, then the data is the point that you have in the HD public key, and then the index, and you do exactly the same thing. The HMAC SHA-512 based on the chain code and the data. Chain code is the shared secret. The point is going to be the self dot point plus big endian to int, the last 32 bytes times g. Right? This ends up working out to be exactly the same. The chain code is the last 32 bytes. The depth is 1 more. The parent fingerprint is the same, and you can make a public key if it's unhardened only. Right? Like you can derive a child unhardened public key if it's an unhardened key. So that's what that looks like. And yeah.
It's kind of weird. So for both of the making an unhardened child and a hardened child, you use the same chain code from above. Is it does it cause any problem to use both of those? Like, so then I make a child for unhardened and a child with hardened with the same chain code. Does it matter sharing that chain code?
Well, the chain code changes at every node because it's derived from the HMAC.
Oh, so at that point it's different.
Yeah.
Okay, so
you're not sharing anything, but at any particular level, the chain code for both the HD private key and the HD public key are the same. That's the shared secret and how the HMAC works. Yeah.
Is the chain code what would stop me from like finding a random public key on the blockchain and then assuming it's unhardened, then deriving subsequent, like trying random indexes? Yeah,
so if you have the chain code and the public key, yeah, you probably could, but generally the way that people use HD public keys is they use the private key, or they don't use the root one. They only use like all of the children of a parent, and you'll see that as part of BIP44. Yeah.
Is the point of chain code basically I could send chain code to Bob, and Bob could derive a child key, and I could technically manage their
Yeah, so the chain code is a way to have a shared secret so that you can derive lots and lots of addresses.
Well, the bot would not necessarily control over.
Yeah. I like as a pair, I don't have any control over it, but it does allow me to derive lots of addresses. Yeah. All right, so here's the path notation, and the idea behind the path notation is that you can go down many levels. So each slash represents like a child, right? So M is like the root master node, and then X is, okay, the xth child index at X, child index at Y, and then child index at Z. So you go to the xth child, and then go to the yth child of that, and then the zth child of that. That's what the path notation indicates. So M1, 2 prime 0 means that the root key's first unhardened child, second hardened child, 0th unhardened child. The slash delimits each level, and the apostrophe or the lowercase h determines whether or not it's hardened. So an apostrophe means that it's a hardened child. Index 2 hardened means like 2 to the 31st plus 2, and so on. But that's the path notation. And this, you've probably seen this with HD wallets. It'll say like, 44 prime, 0 prime, or 1 prime, something like that. And that'll represent a particular path. And these are, we'll get to what that means with BIP44. All right, so here's how you do private key path traversal. So if you have an HD private key, and we have a master, and we want to go down 0, 1 prime, 2, 3 prime, we split it along the slash, right? And ignore the very first one because that's just an M. And based on the component, you go down that particular child. So you go down on that index. If it ends with an apostrophe, then it's a hardened child, so you add 2 to the 31st. Otherwise, it's just a child index. And you can use this to traverse down the particular derivation path, essentially. This is what's called the derivation path. And once you get to that child, again, you can create an address of any kind because there's a private key associated with that particular child or descendant. All right, so yeah, I bet you this one's written for you, right?
I think
I'm really sorry about this, but you can go look at what traverse looks like. So here's traverse for HD private key. You start with self, and then you split the path, and then you go through the components. And if it ends with an apostrophe, then it's a hardened child. So you add 2 to the 31st, and you ignore the last character and make it into an integer. Otherwise, it's just an integer, cast it to an integer, whatever the component is. And then you go down one level at that index, and you already have written the child method. So you do the same thing for each component. So you can go down like many levels, right? And in fact, this is like used as security sometimes. I think Michael Flaxman's idea of like using some random pathing to determine where the private key lies is a particular use case. But anyway, you can traverse whatever path you want, and you'll get the node at that particular place. And you have the private key there, and you can sign something if you know the derivation path. And this is where like HC wallets get a little tricky, because you need to know the derivation path in order to know where your private key is. And if you lose that, then you lose your private key essentially. So you have to be kind of careful about keeping metadata around. But that's why BIP44 exists, because there's standardized pathing to know where something goes. All right, so serialization. All right, yeah.
Sometimes in the path, instead of prime, includes a lowercase h. Is that
Yeah.
part of protocol, or is it just something that?
That's just convention because like an apostrophe is annoying from a coding perspective, right? So it'll be like 44H or something like that instead of 44 prime. All right, so serialization. So oftentimes you want to pass these, HD public keys or HD private keys around, and in order to do that, you need to, have some readable way to do it. So HD key serialization, BIP32, YPRV, YPUB standard is defined in BIP49. ZPRV, ZPUB standard is used in BIP84. They're used for the different types of addresses. So 32 defines for pay to pub key hash, 49 determined for pay to script hash, pay to witness pub key hash, and 84 for pay to witness pub key hash. I think it's a little bit of a mess, and I think they wanted to come up with one for pay to taproot and stuff, but the thing is, like, most of the time you don't want to have like a different standard for each one, or have like another letter used, right? Or like Xpub, Ypub, Zpub, and for testnet you need like Tpub, Upub, Vpub, and all this other stuff. It gets really bad.
But
yeah.
The general word is still Xpub. Like in Xpub refer to all of them still.
Yeah, kind of. It's linguistically a bit of a mess. All right, so here's what an Xpub looks like, and this captures all the components of an HD public key. You have a version, and these 4 bytes are there for a particular reason. Then you have depth as 1 byte, parent fingerprint as 4 bytes, child number as 4 bytes, big endian, chain code as 32 bytes, compressed sec as 32 bytes, and then the result is base 58 encoded. And base 58 encoding is used in for pay to pub key hash and pay to script hash addresses. It's very similar. And these 4 bytes correspond exactly to the letters after base 58 encoding given the same length, XPUB. That's where you get the word Xpub from. And that's why we have that version. It's so that after you base 58 encode it, it always starts with XPUB. All right, so here's how you create an Xpub. So you always start with those 4 bytes so that you end up with XPUB. You do a 1 byte depth, so I guess you can't go down more than 256 levels. Then the parent fingerprint, then the child number in 4 bytes, then the 32 byte chain code, and then the 33 byte public point. And then you encode base 58 checksum on it, and you can see what that looks like in your Jupyter notebook. So let's see, example. We already did this. Path notation. We already did the traverse. So if we do this, then we get what looks like an Xpub, right? XPUB 661 blah 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 blah. It's kind of long, right? But that's what Xpubs look like. XPRV is the private key version of this, and everything. The version's a little different. These corresponds to the letters XPRV after you base 58 encode it, and then the private key is in 33 bytes instead of 32. It could be encoded in 32 bytes, but to keep the length the same and to have it start with XPRV, we make it this way. And you can actually do exercise 4 because it's not there. All right, so finally you get to do something. And it is like we've already gone through 45 minutes. All right, so make your own passphrase. I suggest just like your email and username, or email and name. Again, this is kind of a brain wallet. But yeah, create an HC private key instance using from seed and make sure you put testnet equals true. And then go through this and then print the base 58, which should start with XPRV, which is how you will know that you have the the right thing. And yeah, so there you go. Give that a shot. Yeah.
Like a few wallets don't seem to use these bits, like Armory and
yeah, Armory doesn't use H. Well, actually, they converted to HD a while back, but yeah. But there are wallets that don't use HD. But yeah, they tend to be older.
I mean, like LND has another one that's different from this, I think, too, right?
I'm not sure. Yeah, which wallet with LND? LND is just like the Damon. They have their own wallet. Almost always, all the wallets require you to back up a BIP39 seed.
Yeah, I don't think there's BIP39 though. I guess I was wondering, like, are there? It seems like 90% of the wallets use BIP39 though.
Mm-hmm.
You don't. But do you have any info on how different the ones that don't are?
I'd have to look at their spec or yeah, how they derive it and stuff. Yeah, I don't know though. But yeah, try this and see if you can come up with your XPRV.
Hey Jimmy, is encoding with base 58, is that kind of like taking ones and zeros and putting it into like hexadecimal?
No, base 58 is, but it's in the book if you wanna look it up. But it's taking the base 64 characters and removing 6 of them, and then using that as the alphabet for encoding it as a base 58 number. And the alphabet used is like basically most of the numbers and letters that exist. So 0 to 9, A through Z, uppercase and lowercase. But it removes like 0, capital O, capital I, lowercase l.
But it is just making like a new format for the same thing.
Yeah, I mean it was used for pay-to-pub key hash addresses. So yeah.
It's not like hashing SHA-256 and getting a...
No, the checksum uses some of that, but yeah. Yeah. So give this a shot, guys.
Maybe you try adding like the directory
Maybe I'll see that file make
You press escape.
I will update this later so that it doesn't have all the answers, so you can try it. But at least this you can do, right? Like this actually requires you to.
Jimmy, can I ask a question about like why, I get why the last, the derivation path, the maybe second to last one wouldn't be hardened so that watch-only wallets could see all the, but why would you not want to harden everything? Or why would you unharden one in the middle?
It's just the options are there according to spec. What you use it for is entirely up to you.
Because when it's raw. So if I have not put raw underneath, then online too.
Oh, okay. So I can go look at the code, find out what I'm supposed to be writing in there. Okay. Good stuff.
So I guess Azure version that makes.
Are you trying to come to me? Are you trying to come to me?
Yeah.
Yeah. Here, I'll come over.
From
This
C.
module.
Yeah, so you're supposed to ask. So I have
But I'm closer than I was before.
So I'm just trying to.
Have you messed with this?
I think it's from.
And he just helped me to understand.
Because I mean, I made things like this
Install.
this season here
Guys,
and
little self-running little things that make
it
it run.
says all the requirements are
So I got
satisfied,
this thing.
but it's not finding that
So
one.
now I have to put in all the right commands in here and then run it and print that
PBKDF?
damn thing out.
Yeah.
So now I gotta find where,
Go in your
where
session,
in there
and I go
is
to
the little code.
this,
And I think
and I
it's in
scroll
the
down.
right, it's in
and I try to run the first one. This one.
See, here's the two things
It says you can't find that
exercise
module.
Oh, wait.
Try pip install PBKDF, or like look up PBKDF2 and see if you can. What version of Python?
Create an HD product. And the version
Should be there.
what you type in version, VER,
Oh yeah, well.
Pip install. Just try it. Pip install PBKDF2.
So do I have to write anything in front of it? Right? Like, or do I just literally write code?
Okay, so Python and then import
So
PBKDF2.
if I say like it's going to add one to one
Yeah,
cell,
down here on the bench, we're making one. Making an extra. We're making an extra.
Yeah, something wrong with your environment. Yeah.
which would be 0, 0, 0, 0.
Maybe Jupyter's not running with the virtual app, so I would enable, like deactivate, activate, and then do Jupyter Notebook.
Oh, so I wonder if I
You might be running like your, not the virtual environments Jupyter Notebook, but
so there's this activate command.
which you didn't do.
I did that, but I did it before I saw the requirements.
Yeah, that would be why.
Oh yeah, because these are the parts. So
That's the parts, you know.
You need to activate and then install so that you're in the same thing, and then just stop Jupyter Notebook wherever it is, and then start it again. All right, guys, let's work on making this work. I'll show you how I would do it. All right, so I am going to put my email in like so. And HD private key is HD private key dot from seed passphrase net equals true. Okay, so raw equals let's see, 0488 AD E4. All right. And then I want int 2 big endian 0 because that's the depth. And then the fingerprint, parent fingerprint is going to be 4 of those bytes. Big endian to int 0 and 4 bytes, and then raw plus equal HD private key dot chain code, raw plus equal HD, it's int 2 big endian on HD private key dot secret in 33 bytes. Print base encode base 58 checksum of raw. What did I do? Oh, into big endian. Oh, I think into byte is better. Right here. Oh, and it is into big endian, not big endian to int. Yeah, there you go. XPRV9, blah 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 blah. You're gonna take a picture in case I have some money.
I can maybe do this at home.
But that's the XPRV, and this is the mainnet one, and for testnet you have a different raw or different version bytes, which ends up with TPub or TPRV, just so you know. And those are in hd.py, where these are all the versions that get you the right X or Y priv or Xpub or Xpriv or whatever, right? Like that's what those bytes ultimately do. All right, test PRV PUB, that's going to be in hd.py, and this is the PRV serialization, which is basically what you just did. XPRV, YPRV, ZPRV, they just use different prefixes for the version based on testnet or mainnet. Similar thing for Xpub. You also have Xpub, YPub, ZPub based on testnet or not. And it uses the same serialization. All right, and then test parse. So parse is going to be taking an XPRV or XPUB and returning an HD private key or HD public key object. And let's see, where is the parse method? I feel like it's gonna be around here. All right. So parse is going to do raw decode base 58. So you go and decode it, make sure it's 78 bytes, create a stream, and then use the raw parse method. Make sure that the version is in one of these PRY or XPRV ones. Derive the depth, the fingerprint, the child number, chain code, secret, which gives you the private key, and then you can create an instance of the HD private key class. Similar thing down here for parse here. You raw decode base 58, create a stream, and then do raw parse, which is going to look very similar, except you're going to do a public key parse instead of a private key parse, and you can create an instance of the class. So that's how you work it. Create an extended public key, create an Xpub on testnet, so you can actually go do that one. So let's try it. It's going to be exercise 7. 5 and 6 should work. And notice how long it takes. It's very sort of like intense in terms of CPU usage. But yeah, using your passphrase, print the Xpub using the Xpub method, and you should be able to do it. So this one shouldn't take very long. And once you're done with that, we'll move on to BIP44.
Can I ask a beginner question?
Yeah.
So in the solving of that last one, watching what you were typing in the middle, that is just understanding that how to ask Python the right questions?
Yeah, to make it do something.
To get it send things out. Okay.
Yeah, yeah.
Because I just didn't know, I didn't have that, you know. And so now that's why I took a picture. Okay.
Well, I mean, it's incompleted too, so
Yes.
you can go look it up.
But the answers were in here, right? If I went into the code, I could find the things I would need to type to get the results.
Yeah, it's all there.
Yeah.
Yeah.
All right, cool.
Yeah.
What is the point of the unhardened keys then? Like, why would we ever put this?
If somebody's paying you a lot of different times, right? So they're settling with you every day. You don't want them to use the same address. If you give them an unhardened account Xpub,
They can automatically do that.
yeah, they can derive as many addresses as they need.
Is there a way to do like a child Xpub?
Just needs a matrix.
Yeah. Yeah, at every node you can do an Xpub or an Xprv.
So would that serve the same function though?
Yeah, and you'll see exactly how most wallets do it with BIP44.
But if you have an unhardened public key, use that to generate
So that's phrase, you can fill that in with something.
This is we could do.
Well, if you leak the Xpub, yeah, that.
But if you're just an unhardened,
That would be an Xpub. An unhardened Xpub, you don't share with anybody except the pair. Yeah. Because the public key doesn't have the chain code. The Xpub has the chain code, which is your shared secret.
so all this Python stuff here, where did you write this just for this workshop or?
Yeah, I mean it's in the BIDL library as well, so you can go look it up.
Which library is that?
BUIDL, BIDL Python. So it's they have similar code in there. All right, here this is how you use the library basically. So here's how I can create my passphrase, and then HD private key equals HD private key dot from seed passphrase testnet equals true, print HD private key dot Xpub, and notice it starts with TPUB because it's on testnet. If you change this to false, then it would start with XPUB. And that's to make sure that you're not using testnet Xpubs on mainnet and vice versa. All right, so that was exercise 7. Now let's talk about BIP44. What's BIP44? We want to give structure to the BIP32 hierarchy. It's too loose, right? Like you can derive anything anywhere. And you can have lots and lots of private keys that do all kinds of stuff. And the idea is that you have different purposes. So 44 is pay to pub key hash, 49 is pay to script hash, pay to witness pub key hash, 84 is pay to witness pub key hash. And you can have different coins. So 0 hardened is Bitcoin, 1 hardened is testnet Bitcoin. But you can also have lots and lots of others. And if you click on this link, you'll see slip44, register coin types for BIP44. You see Bitcoin and testnet. You have Litecoin as 2, Dogecoin as 3, Redcoin, Dash, Peercoin. You could literally store every kind of coin on this list with just one seed phrase. And that's what most of these multi-coin wallets use, is a single seed phrase, but this is at the level where they distinguish, okay, this path is only for Litecoin, and so you can do something like that. Account is a hardened child that corresponds to a pair, and the account level is meant to be separate per pair that you have. So if you have 5 different pairs, you have 5 different accounts. And many wallets will just use 0 and not give you options for more than that. But if you use something like Trezor, you can have up to 10 accounts, even though the spec makes it so that you can have lots and lots. The thing is, like, recovery becomes tricky then, because then you have to check like every single account to see if they have any coins in it, and that just makes searching for it really difficult. Chain, unhardened child corresponding to receive addresses and change addresses, so external, internal. The idea is that if you're creating your own transaction, you have change addresses, so you don't want those mixed up with receiving addresses. So your payer will give you money to your receiving address, but not to your change address. And then address, it's an unhardened child to get the actual child from where you derive the actual address. Yeah.
So if I'm making a transaction to someone, and I'm taking the Xpub and I want to like derive a change address as well, do I use the same index as I'm using, or like how does that work? Because I don't want to like get them mixed up or accidentally send
Yeah, so the change addresses have their own index. So as you create more change, you keep incrementing the one counter, and then the external addresses have another counter. So
do those move together? Or?
No, they move separately, and you have to keep track. And this is where like the HD wallets kind of suck, because if you're recovering it, you have to like go and search them all, right, up to a certain point, and you have like these gap limits and stuff. Okay, like sometimes you use these addresses and nobody pays them, but you've burned it because you've given it to somebody. You don't want to reuse it, so sometimes you have like large gaps. So this is where like recovering from a particular seed can be very tricky. Yeah, kind of sucks. All right, so here are some examples. So this is 44 is the purpose, and that's always the first level of BIP44. It's 44, 49, or 84. So 44 is pay to pub key hash. 0 prime is mainnet. First account. External is 0, and then the first has already been 3 change addresses used, so this is the 4th address. So this is the derivation path for that particular one. The third one is pay to script hash, pay to witness pub key hash. It's mainnet Bitcoin, 0 prime, and then the second account, internal, which is a change address, and then the first change address for that particular account. Then the last one is pay to witness pub key hash, and it's the first, it's testnet Bitcoin, first account, external, and the third address, right? And it assumes that you've already received 2 addresses. So these are some examples, and there's, you can obviously create as many addresses as you want under any of these. But that's what this looks like. So here's an example of getting a pay to pub key hash, pay to script hash, pay to witness pub key hash, pay to witness pub key hash testnet addresses. You create the master pub key, and then you have this derivation path. You traverse to that path, and you ask for the pay to pub key hash address. You go to that particular path, which is for pay to script hash, pay to witness pub key hash, and you ask for the pay to script hash, pay to witness pub key hash address. Similar thing for the BIP32 address at this particular path. And you can go to the Jupyter notebook, and it will give you, testnet versions of each. So pay to pub key hash addresses always start with M or N on testnet. They start with 2 for pay to script hash, and TB1 for pay to witness pub key hash, and there are certain lengths. So you can see that this looks reasonable, right? Like that's how you derive addresses given a master seed phrase. Yeah.
So, do you ever have? Does the tree stop at that many levels? Like
yeah, for this, yeah.
So people would, if you gave them your Xpub system, they'd only increment the index. They would never add another level.
Yeah, they don't add another level. If they do, they're making a mistake, and you're not likely to receive it. So that's how it works, and these are the derivation paths that most wallets use. Okay. Get address basically codifies that. All right. So exercise 9 is create some addresses. Go try it. There's a method already kind of written in the previous exercise, which is get address, I think. Let's see. Yeah, get pay to pub key hash receiving address, get pay to pub key hash change address, get pay to script hash, pay to pub key hash receiving address, and so on. And they figure out the path that it needs to go on, and you tell it, the address index is the very last one, and these are set to 0, so it'll only give you the first one, but you can increment that or change the account number and so on, and it'll derive the right thing. So give that a shot. You're learning how to use the library, basically. Yeah, this is where Shift tab or get. Yeah, it'll give you all of these names, so you don't have to type it. All right, so here's how you do it. You print HD private key dot get, and then if you press tab, it'll give you the method name. HD private key dot get, press tab, and you can do that one too. And then HD private key dot get. Yeah. And those are some addresses that you can use. Now, like constructing a transaction using the private key that's stored in there is something you can do as well. Haven't written any things on that, but you can also create an Xpub for a particular account, and that's what we're going to do next in exercise 10. This is what you would give to somebody to say, okay, you're going to pay me frequently, here's the account, you keep track of the indexes, and I will be receiving them. So every time they need to pay you, they increment that index, derive the address, and then pay you at that address. And you, being the recipient, will detect that and go and do, spend it as you need to or whatever.
So this is where you would use unhardened.
Yeah.
Specific.
Yeah. Well, you use hardened all the way down to a particular, and then you give them the Xpub, and they do the unhardened derivation using the Xpub.
Because you don't want to give them.
Yeah. You only give them the Xpub. What's that? Yeah, so the chain code is included in the Xpub. All right, so here's how you do this. All right, we need the private key. And then we calculate the path, which is going to be m/44 prime / 1/, which is the coin, and then 1 prime, and then 0 prime for the 0th account, or the very first account. So we do node or
It's testnet, right?
yeah, 1 prime is testnet, right? So
Isn't that big? Oh, sorry.
yeah, so we do HD print HD private key that traverse that path, and that'll give us the node that we need, and then do Xpub. And that's what we would get. This long ass thing is going to be, it encodes the chain code and the public key at that path, along with everything else. So at that point, they can do an unhardened derivation of the public key for external, internal, and then the index at 0 or whatever. And using that, they can pay you, right, on a continuous basis. Many different times using this one thing. This is sort of like the super public key that they would get. At least this is how it was intended to be used. Most wallets don't use it this way, which is interesting. But the way most wallets use accounts is I have, accounts for different people for like a particular Trezor wallet or something like that. And many of us hold money for our relatives, right? So you use account for one for me, and one for mom, and one for my sister, whatever. And you have many different accounts, and that's how they get used, not in this particular way, which was the intention. All right, so we're coming to the mnemonics. Okay, so how does the mnemonic backup stuff work? All right, what is a mnemonic backup? It's a way to back up HD wallets And it's way easier to remember than anything that's base 58 encoded. So instead of memorizing the XPRV, you memorize a bunch of words. It uses 2,048 English words whose first 4 letters are guaranteed to be unique. Okay? First 4 letters are guaranteed to be unique. Each word stores exactly 11 bits of information, because 2 to the 11th is 2,048. And there's 1 checksum bit for every 32 bits. So that way it works out that if you have some multiple of 3 words, then you're going to have exactly the right number of checksum bits. So what does that look like? It's defined at BIP39 and specifies the mnemonic backup standard. And it has an optional passphrase for more security. So you can have a second factor authentication, which essentially makes it 2 of 2 for a passphrase. Different numbers of words corresponds to different amounts of entropy. So you could have 12 words or 24 words. 12 words corresponds to 128 bits. 24 words corresponds to 256 bits. And it's very hard to brute force even at 12 words. Now, 12, 15, 18, 21, and 24 words are allowed. It has to be divisible by 3 just because the extra checksum bit, 33 divided by 11 is 3, so like 3 words go into, 3 words correspond to 33 bits, which stores 32 bits of information. I've never seen anything other than 12 and 24, but 15, 18, and 21 are available as options under the BIP39 standards. And 2 to the 128th is still an enormous number, so you can't really brute force it. Whoops. All right, so here's how you actually generate a mnemonic. You start with a random number. It's 128, 160, 192, 224, 256 bits. In practice, it's just going to be 128 or 256. Divide the number of bits by 32. That's how many checksum bits end. So for 128, that's going to be 4 checksum bits. For 256, that's going to be 8 checksum bits. Checksum is the first n bytes of the SHA-256 of the random number as a big endian integer. It's a little bit of a mouthful, but there's a formula for calculating the checksum. Combine the bits and checksum to produce a bit array. And you get basically 250, for 128 bits, you get 4 extra bits for checksum, so that's 132 bits. 132 bits is going to be encoded into 12 words, right? 12, each bit is 11, 12 times 11 is 132. 256 plus 8 checksum bits is 264. That divided by 11 is 24 words. That's how you get the number of words. And here's what that looks like. If we have, I don't know why the top isn't showing there, but you can see the number of bits. And basically you create you create a random number. You get the number of checksum bits needed. You calculate the checksum. You add it to the bits list. And then you take 11 bits at a time and come up with the word that corresponds to those 11 bits. And that becomes your mnemonic joined together with a space at the end. And here's how you create a mnemonic. Yeah, can you tilt it down a little bit? All right, so here's the mnemonic: legal, winner, thank you, or whatever, and those are typical words. and you could put a password. So Trezor developed this standard, so all of their test vectors have the password Trezor in it. But you split the words, and then you make sure that it's one of the allowed number of words. You look up the word and get the number associated with it, and then make a long bit length thing. And then you do a SHA-256 of the actual data and make sure that the checksums match. And if the words fail the checksum, you let them know. And then you need to normalize the word. So it's possible that they just give you the first 4 letters of the word. So a lot of seed backup things will only let you put the first 4 letters. But what you need to do is have the whole word in order to actually derive the HD private key. Once you have the whole words, you have a salt, and you have this function called HMAC SHA-512 KDF. What does that mean? You know what an HMAC SHA-512 is? KDF stands for key derivation function, and it's a way to make it hard for you to brute force, and the library you're using in Python, which is standard, is called a password-based key derivation function, and this ends up being the password. The normalized mnemonic is essentially your password, but it's meant to be very hard to brute force. So it uses like 2,048 rounds of HMAC SHA-512. So if you want to try many different ones, it doesn't scale very fast. So it makes it very different and difficult for you to brute force anything, because it already takes so many CPU cycles, because it does that many rounds of HMAC SHA-512. But that's what that is. And then once you do that, once you do the HMAC SHA-512 on the KDF, you get the seed, and you use the from seed function to get the XPRV. So that's how you go from a mnemonic to an XPRV, or the actual HD private key. And if you do have a password associated with it, it goes in the salt, which kind of like the Bitcoin seed, space seed. It's always mnemonic and then plus the password, or if it doesn't have a password, it's a blank, so it's just mnemonic, and that's your salt that you use for your password or for your key derivation function. And then you get the seed, and then you can derive your XPRV, and that's how it works. So it's a little convoluted. I don't necessarily think this was the best standard, but it's the standard that everyone uses, and it's used by every wallet and so on. I don't necessarily think the 2048 word list is great either, because some of them are 3 letters, so you have a blank 4th letter and stuff like that. So I think air, for example, is a word on the list. There's an alternate list that uses only all words that are 4 letters or more, so that you always fill it up. But there's all sorts of things wrong with these standards, and we only find out about them after we've been using them for a while.
Thought you were going to say list of 4-letter words.
No. All right, so the from mnemonic is written for you, and this is sort of your final exercise. We're gonna use everyone is going to use the same mnemonic. Abandon, and I think what's the last word in that? I think it's right here. About is the last word. So abandon is the very first mnemonic word, in that list of 2048, because it's in alphabetical order, and the very last one has a checksum, so it's about. But basically, I want you to come up with an Xpub, at 84 prime 1 prime 0 prime. So it's the very first account that's using pay to witness pub key hash addresses. And the difference here is that you're going to use a passphrase locking it to this mnemonic, which you can do as well. This is an alternate way to do a brain wallet. You can just give the seed phrase straight to the from seed thing, but if you want to if you want to be compatible with lots of other wallets, this is an alternate way to do it, is to use a known mnemonic and have your own passphrase, right? So this is an alternate brain wallet. None of them are recommended, by the way, but you can do it this way if you want to be compatible with, sort of existing wallets and so on. So, but yeah, give that a shot. This is the final exercise. So, yeah, it's. What's that? I can't hear you. Yeah, I think you can add a passphrase to it, and it only uses hardened derivation. So even after the account level, external, internal, and address index, they all use hardened derivation, at least in Bitcoin Core.
So I could export my XPRV and then run through this. I don't know.
Argument.
If you have the XPRV, so you can derive the XPRV from your mnemonic and passphrase, but you can't do the other way. You can't take the XPRV and go backwards to the mnemonic because it uses a hash function.
So I wrote that.
That's fine.
But
Yeah.
here after
I guess I'm trying to figure out why Bitcoin Core doesn't give you a mnemonic.
I think so.
Oh, I don't know.
And I guess I'm wondering, so I can't generate one myself with this.
No, you can't. You can't go from a mnemonic to. Well, you can go from a mnemonic to an XPRV. You can't go the other way. I don't know how Core derives it, but yeah. But this is the standard just about everybody uses. So.
And that's basically because of the free seed. You have like a free seed in here, just random bits that are XORed with entropy.
Yeah, that's something that you can add your own entropy if you want in there. That's part of the spec, is that you're supposed to. Otherwise, the test spec, it's hard to test it. So.
Do you have any examples of what the seed looks like in binary form?
The seed.
Like this one right here,
Oh, it's all zeros. It's zero. Yeah, all the bits are zero. Abandon is like the very first one, so it corresponds to 11 0 bits.
So that would be 0.
Well, I mean that's the entropy that would derive this mnemonic, but this mnemonic derives a completely different XPRV. Or I mean, the XPRV doesn't have zeros in it.
Can I convert that to a decimal? This binary form of mnemonic?
Yeah, the thing is, you need the mnemonic in order to you need to put it into your HMAC SHA-512 KDF function. So you hash these actual words. Yeah. Like I said, I don't necessarily like the standard very much. But, all right, so here's what I'm going to do here. Jimmy at programmingblockchain.com. and we can do HD private key equals HD private key dot from mnemonic passphrase path testnet equals true, and then print HD private key dot Xpub. There you go. And if I had that, I could send you guys some money, right? Like on testnet or something like that. All right, so that's about it. I apologize for some of the hiccups in the thing, but you guys knew that you were guinea pigs, so I don't feel too bad. But yeah, hopefully you learned something. If you have feedback, email me at jimmy@programmingblockchain.com, which I've been writing over and over in this thing, so you can send me your thoughts if you are so inclined. But yeah, that's about it. We ended a little early because, of course, there was a lot of the exercises couldn't be done. I will update it so that they're not done, and you can go and try to actually code this stuff. There you go.
Nice. Thanks, Jimmy.
Thank you.